Okay, I think I'm ready. We got some people online, I guess. Okay, somebody online, just type into the chat box, say hi so I know you can hear me and see my screen. And in the meantime, I will get started. I'm going to assume that it's working. It's working here, so I'm going to assume that it's working overall. Let me mute everybody except me. Okay, yep, that seems to be working. Okay, thank you. I did get some responses there. Okay, there's a document on Blackboard called Session 9 Lab Exercises, T-Test, paired, single sample, paired, and independent and paired T-tests or something like that, something similar. It's the only Word document there on the data files. You might want to open up because it has a bunch of examples I think we can try together to maybe get a little bit of practice doing these calculations. Just for starters, I'm going to do a very little quick backup on this. You guys remember confidence intervals? We calculated confidence intervals by looking, when we took a sample from a population, we were interested in finding the population mean, right? And standard deviation is really what we're interested in, but we rarely know those, unless it's a census and sample the entire population. Generally, we just know the sample mean that we calculate, the size of the sample that we use, and the standard deviation for that sample. And we do that because we know that if we get a decent sized sample, that in general, the sample mean is going to approximate, or we hope it's going to approximate, the population mean, and the sample standard deviation is going to approximate the population standard deviation. Okay, and so when we take a sample, I'm going to take a sample size 100, let's say, nice big sample. And when we take a sample, we say to ourselves, well, we now understand the dynamics of how a properly applied sampling works. And we know that if I take a sample of that size, that I can expect that those samples are going to be distributed in a manner that's going to be consistent with the way the population is spread out, the way sigma is for the population, right? But they're not going to be spread out as much as the population is because each sample mean is going to be closer to the population mean. So if I take repeated samples over and over and over again, well then the distribution of those samples about the mean, the population mean, distribution of those samples is going to have its own standard deviation. We call that standard error. And that's equal to the standard deviation over the square root of the sample size. Right? Only problem with that is that really to know that I have to know the population standard deviation. If I don't know the population standard deviation, I'm forced to use what I do know, which approximates it, but is not exactly the same thing, which is the sample standard deviation. So our standard error becomes S over the square root of n. So we know if we know the population standard deviation, or if we could, we know that if we took repeated samples from a population that has a mean of mu, that 95% of those samples of that size are going to be within roughly two standard deviations, really 1.96 standard deviations of that mean, whatever that mean is, right? So 95% of the time, we're going to get a sample mean that's going to be in that range. Every once in a while, 5% of the time, we're going to get a sample mean from that population that's outside of that range. That's at the more than two standard deviations below the mean, or less than two standard deviations below the mean. But we're willing to say to ourselves, it's unusual. In other words, it only happens 5% of the time for us to get that extreme result if we take a sample of this size from this population. Okay, so we're willing to say that if we take a sample and it's that different from the mean, we're going to reject, and we take a sample from another population, And it's so different from that mean that it would only occur if we're outside of that 95% interval that we expect we would get, if we from a sample from that population or population that has the same mean and distribution, right? Well, we're willing to say that the mean for that first population doesn't equal the mean for the second population, or at least we're willing to throw away the idea that the two of them are equal, right? And we think that we can do that because, well, there's less than 5% chance of being wrong if we do that, because we'd only get that outcome less than 5% of the time, even if the populations were the same, right? So we're going to take advantage of that. Okay. Now, the only other thing that we have problem with is that, and we know that 2 standard deviations is really 1.96 standard deviations. If we're interested in 95% confidence of being right about what we do, in other words, 5% chance of being wrong, making a type 1 error, and improperly rejecting the null hypothesis, which says that they're equal. The two means are equal. So we're willing to accept that level of error. The only problem now is that was all based on the fact that we knew the population standard deviation. Most of the time we don't. We have to work with a sample standard deviation. So that's very sensitive. How well we know that is very sensitive to the sample size. So instead of 1.96, we have to accommodate for that extra level of uncertainty. So instead of using that z-score that we've been using to correspond to 95% confidence, we have to use a t-value, right? And there's a different t-distribution for every different sample size, right? Well, we don't want to work with a textbook that's got 5 million tables for every possible sample size. So instead, we use a t-table, and that t-table only has the really important t-values that we're interested in. The t-value that corresponds to 1.96 or 95% certainty for our particular sample size. So we have sample sizes here, degrees of freedom, but effectively sample sizes. And we have columns that indicate the critical value of t that we need that represents 95% of the possible outcomes. And these t-values are always going to be a little bit bigger, somewhat a little bit to a lot bigger than 1.96 for 95%, because we're using the sample standard deviation instead of the population standard deviation, right? It's pretty abstract so far, okay? We're going to try and apply this now. Okay, so if we open that document, I'm going to open up that document on my machine. Okay, let me find it. And we're going to give it a try. Okay, so let's take a look at this. On my machine, for some reason, Microsoft Word has to warm up. It's like my car. I started in the morning, so I got a computer in it now. I started in the morning. I have to wait for it to boot up. It used to be I turned the key. Now it's a computer. Okay, so I'm going to take a look at this first example of a single sample test, single sample hypothesis test. Okay, and in this situation, I'm going to say that we know what the standard deviation is. I'm going to work this out, and then you guys are going to work out the second one with a little bit of guidance from me. So in this sample, in this situation, I'm saying that I take a sample from a population, right? It happens that I get 9 values. I'm ignoring units, and I'm not building a story around it. I'm just going to work with numbers for now. You can see that, right? Okay, I'm going to say that sample size, that's the sample size of 9. I have 9 values from that sample, numerical variable. And I'm going to say that we know what sigma is. Sigma happens to be 3. The population standard deviation that this is taken from is known to be 3. So now I'm going to test that and see if it's the same or different from another population where I know that the mean, the true population mean, is equal to 8. Okay, and the level of certainty that I want, the level of error that I'm willing to risk is 5%. Type 1 error is going to be, or alpha is going to be 0.05. So what do I know here? I'm going to pull up Excel. I'm going to pull up the same file in Excel. Okay, and it's also on Blackboard if you want to work with it. Okay, let's see if this takes a few minutes to warm up. No. Okay. Excel has the same issue. Okay, we should be okay now, by now. Okay. Single sample test. Oh, hang on a second here. Okay, here's the numbers that I have. Let me center them a little bit, make them a little easier to read. Okay, so these are the 9 values that I have. So what do I know about this? Well, I can calculate the mean for the sample, x bar, right? I know what the sample size is. I know what sigma is equal to. Okay, I know sigma is equal to 3. That's been given for us. I don't need to calculate a standard deviation using this sample. And I'm going to want to know what the standard error is equal to. Okay, anybody? I also know what alpha is, what my level of acceptable error is, 0.05. Okay, anybody want to tell me how I calculate standard error if I know sigma?
Sigma times square root of
Sigma over the square root, right? Square root of the sample size, right? 9. Okay, so that's equal to 1, right? Turned out to be 3 divided by the square root of 9, which is 3. So that's equal to 1. Sample size is 9. Okay, so that's my standard error. So what are the things let's calculate what the mean is. Mean is just a simple arithmetic average for all these values. And that's equal to 9.88. Okay. So now I want to say to myself, well, you know, this is the population that I am sampling from, right? Population where I don't know what mu is. Mu is unknown, right? I'm comparing it to another population that I do know what mu is. Mu is equal to 8. I think I assigned it 8, right? Is that what's in that paper? Or was it 6? 8. Okay, it's 8. All right. So now I can say to myself, well, how likely is it that if I took a sample from this population, where I know the sample, value of the mean of the population is 8, how likely is it that I would get this extreme of value, 9.8, if I took a sample of 9 people from that population? How likely is I would get that far apart? Well, if we remember how first of all, number 1, the distribution of repeated means of sample size 9 is going to be normally distributed, right? Why is it going to be normally distributed? What rule is that? What theorem is that? Central limit theorem, right? Actually, 9 is a little bit of a small sample. We would like something bigger, but in general, the bigger the sample is, the more likely that the distribution of means is going to be normally distributed. Okay, and the less reliant we are on the actual population being normally distributed. Okay, so population mean is 8, for the population we're comparing it to, but the sample that we took from the unknown population is 9.88. Okay, so we could actually calculate a confidence interval for that mean, right? And we could actually see if that confidence interval includes the value 8, right? To see if it's within that 95% confidence interval for what we think the true mean is for the first population. But there's another way we can do this too. And what we can do is we can actually calculate the number of standard deviations apart that value is from our 2 population means appear to be apart, right? In other words, the number of z-scores, or in this case, a number of z-scores because we know the population standard deviation, right? So in order to verify that these 2 populations have different means, I have to prove that there are at least 2 standard deviations apart, right? So let's give that a try. How are we going to calculate that? Well, in our case, I'm going to use z, right? Because I know the population standard deviation. If we were to do this without knowing what the population standard deviation was and having to rely on the population standard deviation of the sample, then I would have to use t instead. Right? So I'm going to say that z is equal to the difference between the 2 means, x bar 1 minus x bar 2. Minus mu, excuse me, you know what mu is for the other population. And what are we going to divide that by? We're going to divide that by the standard error, okay, which we calculated, or which we know, right? So what is z going to be equal to? Z is equal to, okay, the number of standard deviation apart that these two values are 9.88 minus 8 divided by the standard error. Okay, now what's the standard error? The standard error is equal to 1. Okay, and I get a z-score of 1.88. Okay, now, what did I need that z-score to be in order to know that I'm enough standard errors, enough standard deviations apart to say that these two came from two different populations? I needed it to be 1.96 standard deviations apart. I'm gonna change this a little bit. I'm gonna make that population mean, I'm gonna make it 7 instead. And if it's 7 instead, right? How many standard deviations apart are there? They're 2.88 standard deviations apart. Okay? So what does that mean? How likely is that to occur? Right? Well, let me get my... And remember, this is all occurring because we know the population standard deviation. So here's mu, right? And here is our value, and it's 2.88. Our z-score is 2.88. It's 2.88 standard deviations away from that other mean. So the probability that if this came from the same population, that we would get that extreme of value is the area that's to the right of that 2.88. Okay. Now the only problem is that when we started, I didn't say anything about knowing ahead of time whether or not our test population is bigger, going to have a higher average or a lower mean than the population we were comparing it to. So I really have to accommodate the same z-score at the bottom, minus 2.88. Okay, so in other words, I have to take whatever this area is and double it. Right? Well, let's look up what that area is. Right? There's going to be a z-table. So a z-score of 2.88. I'm going to start with negative 2.88. It's going to be easier. Negative 2.88. Let's see, next to the last one is going to be 0.002. That area is 0.002. So that means that this area is 0.002. So the probability of getting that extreme a difference between these two means is going to be 0.004. I'm going to call that P. That's the probability of getting that extreme a difference between the two means if the two populations really have the same mean. Okay? So let me take another step back here. If I had set this up as a hypothesis test, what would have been my null hypothesis? What am I starting with? Well, I'm starting with the prospect that they're equal to one another. Mu-A is equal to mu-B. Right? In one case, I know what the value of this is. It's equal to, after our adjustments, equal to 7. In other words, we're starting with the proposition, the null hypothesis, that mu, that this population we're taking the sample from, is equal to 7. Okay? What's our alternative hypothesis? That it's not equal to 7. Right? So now, with this result, that based on what my mean was, which was 9.88 x bar, based on the mean that I got from my sample of size 9, how likely is it that this really came from the same population? Well, there's only 0.4% chance that it came from the same population, right? So that means that's the probability I would be wrong if I reject the null hypothesis and accept the alternative hypothesis. Can I do that? What was what did I define as my acceptable level of error? 0.05. So I'm way below 0.05. So that's acceptable. Am I certain to be right when I reject the null hypothesis? No, I'm not. I'm never going to be certain that I'm right, but at least I know that there's less than 5% chance I'll be wrong if I do reject my null hypothesis. Okay, so now you guys are going to do the same thing, except I'm gonna change it up on you a little bit too. I call this one 7. Okay, I'm gonna say on yours, excuse me, sample size is 9 still. Okay, let's see. The test population, the second population, I'm gonna call it 7.5. Make it 7.4. Okay, see if we get an interesting result there. Okay, so first of all, number one, what's your null and alternative hypothesis? Anybody want to hazard a guess? The mean for population A is equal to the mean for population B, right? So now, what we know what the mean for population B is? What is it? It's 7.4. So we could either say mean for population A is equal to mean for population B, or we could say mean for population A is equal to 7.4, since we know what that is anyway. So this is a single sample test. So now, remember, now what did we do next? Our alternative hypothesis is that they're not equal. And then we went about calculating. Calculated the mean, x bar. We knew the sample size. We calculated we calculated sigma, or we looked up what sigma was. We were told sigma was. We can't do that now, can we? We have to calculate the standard deviation and use that to calculate our standard error. Okay, so I'll give you guys a few seconds to do it, and then we'll do it together. So calculate your mean, calculate your what your standard deviation is in place of sigma, calculate your standard error, and then we'll calculate, but it's not going to be a z-score anymore, is it? It's going to be a t-score now because we don't know what sigma is. Okay, so now, one of the things about if we know the standard deviation, we can always use z, regardless of what the sample size is, because we know the population standard deviation. If we don't know the population standard deviation, we have to use t instead, the t distribution instead. Okay, so in order to simplify calculations, sometimes what we'll do is that if the sample size is very large, we will say, well, you know, it's going to be so close to t, and we'll look at this when we get to the end of this problem. We'll look at this on the t table. The sample size is very large. The t distribution is very similar to the z distribution, and the value I need to exceed to get those tails to be less than 5%, 2.5% on each side, 5%, is very close to 1.96, just like the z distribution, the normal distribution. Okay, so with a very large sample size, we're tempted to just say, let's calculate z instead. Well, what's a big sample size? How many of you guys drive? You know the signs on the side of the road, they say 55 miles an hour, right? That mean you always go 55 miles an hour? No, right? You go whatever you think is safe for the conditions, right? So there'll be times when you're going for more than 55 miles an hour. In statistics, that sign says, if you don't know sigma, use the t-test. But, you know, it's like 55 miles an hour. You want to get there a little quicker. You take a little shortcut, but you have to make a judgment. What's a big sample size? A big sample size, like 100, is a nice big sample size. When we look at the t distribution, you'll see that the value of t that's equivalent to 95% confidence for compared to the z-score is very close, right? Sample size, the t distribution, z distribution, the sample size is 100. Many textbooks will tell you that, gee, you know, if you got a sample size over 30, you might want to consider just using the Z value, that 1.96, right? Do you really want to do that, in real practice and stuff like that? Well, you got to kind of make a judgment. Some of you guys, when, you'll go 90 miles an hour. Some of you guys will go 60 miles an hour, right? But you have to be aware of what you're doing when you do that. You sacrifice some probability. You increase your probability of incorrectly rejecting the null hypothesis when you do that. Now, should you ever use Z when you're dealing with a sample, right? Well, in fact, SPSS are the most of the time you're going to be using software to do this, and the software will never substitute 1.96 when you don't know the population standard deviation. It will always use the t-test, right? T distribution, but it can afford to, right? If the sample size is 1,000 and the t, the critical value of t for 95% is 1.966, software is still going to use 1.9600001 because it can, right? It's not any harder for it to do that calculation than to round it off. And for us though, it's convenient to round things off, make calculations simpler. But in reality, it obeys that speed limit sign. Okay, so I think I killed enough time here. So okay, let's give this a try. So now what's going to change here? Well, let's see. X bar now is going to be equal to, it's going to be equal to the same thing. Nothing's changed, right? So that's going to be the same. Okay, the sample size is going to be the same. Uh-oh, now standard deviation is going to change. The standard deviation is going to be the standard deviation of the sample. And that turns out to be 2.93. Pretty close, but not exactly the same. That's the standard deviation of our sample. And it approximates sigma for the population, but it's not exactly the same thing. So alpha is going to stay the same. Our level of our tolerance for an alpha error is the same. But our standard error now is going to be a new number. Right? What's our standard error going to be equal to? Well, we don't know sigma anymore, so we have to use the standard deviation of the sample divided by the square root of the sample size. It's going to be close, but not quite the same. Okay, and that comes out to be 0.9781 instead of 1. Okay, so now let's calculate our t-value. And now it's a t-value, right? But it's going to be the same formula, basically the same formula. T is equal to x bar minus mu over the standard error, right? So it's a number of standard errors apart. So our t-value is going to be equal to x bar minus mu, which is going to be x bar minus 7.3 in this case. Did I say 7.3 or 7.4? 7.4, okay. 7.4. Put that in parentheses so it does the subtraction first, divided by the standard error, which is our new standard error. So t is going to be equal to 2.5. Okay, so now can I reject my null hypothesis? They seem to be pretty far apart, right? Right? Well, that's bigger than 9.6. Is it enough that it's just bigger than 1.96?
No, you will compare with the t-table.
Exactly right. I can't use 1.96 anymore. I have to find the value of t for that sample size, which is sufficiently far apart for me to say that those two means are not equal to one another. So now I'm going to go to the t-table. Okay, you have copies of these on Blackboard as well. Okay, here's our t-table. Now, the way that we avoid having to deal with having many t distributions, like the z distribution, is this table only gives us the important values of t. In other words, the value of t that we need in order to know what represents 95% of the sample distribution. Okay, so what was our sample size again? It was 9. Unfortunately, this doesn't use sample size, uses degrees of freedom. So degrees of freedom is sample size minus 1, which is 8. So for 95, for an alpha is equal to 5%, or 95% confidence, we need a t-score. We need to exceed a t-score of 2.306. Did we exceed that critical value of t? T critical is equal to 2.306. So does our t-score exceed the critical value of t? It does. That means we're further away than we need to be to make those tails less than 5%. All right?
So accept the null hypothesis,
We reject the null hypothesis because they're far enough apart. If my t-score had been 1.54, that would mean that our two means, our sample mean and our population mean, are too close for me to distinguish them with 95% certainty, right? We want the t-score to be large. We want them to be, when we say a t-score of 3 or 4 or 5, that's the number of standard deviations, standard errors apart that the two means are. So the further apart the means are of the two populations, the known mean and the sample mean, further apart that they are, the more confident that we are that they're not equal. The two population means are not equal. So we want a t-score that's bigger than the critical value of t. When the t-score is bigger than the critical value of t, what does that tell you that the p-value is in relation to alpha? The p-value is bigger or smaller? Smaller, right? They go together. Bigger t-score, smaller tails, in other words, smaller p-value. A lower probability that you're wrong if you reject the null hypothesis. Okay, so what we knew, there was one sample here. This was easy, right? Because only a single sample here. Now, most of the time, we're not going to be in that situation. We're going to be comparing two samples. We're going to sample A, sample B. We're going to have one group that has an intervention, one group doesn't have an intervention, one drug group that gets a placebo, another drug group that gets the drug itself, and so on and so forth. So very frequently, we're going to be measuring two populations. So there's another file on here called a two sample t-test. I'm going to open up the Excel version of it first. Okay, so here it is. It's broken up into males and females. This could be, I don't know, these represent, who knows, liver function tests, whatever, right? I'm not really that concerned right now about the background story on this, but I have two samples. One is from a population of males, 9 people, one from a population of females. Well, now I want to compare the two means. Before I compared X bar to a known mu. Well, in this case, I don't know any mu, do I? I know I can calculate X bar for males, right? And I can calculate X bar for females, right? But I don't know the true means of either population. This is a two sample t-test. Okay, now let's see. What about sample size? Okay, sample size. I know the sample size. Sample size in both cases it happens to be 9. Doesn't have to be an equal sample size, right? It can be different size samples. So the average for males is 10. Average for females, X bar for females is 7.5. And now, before I go any further, I have a mean here and a mean here, but I'm not really interested in the sample means. What I'm really interested in the population means. So I'm going to set up a null and an alternative hypothesis. Okay, what's my null hypothesis going to be? Mu for males, right? Is going to be equal to what? Mu for females, right? Okay, what's my alternative? Yep, does not equal mu for females. Okay, or you could also put it the other way, mu for males minus mu for females equals 0. Same thing, right? No difference. Okay, so now, in order to prove that, what level of confidence do I want to have? What tolerance do I have for error, for rejecting the null hypothesis incorrectly, a type 1 error? Alpha? Yeah, why not? Let's do 0.05. Doesn't have to always be 0.05. It's a really critical analysis. You really don't want to be wrong. You could make alpha 1%. right? 0.01. But most of the time, you'll see in publications, you'll see 5%. Okay, you'll also see a lot of times that people will try to replicate studies, and 1 out of 20 times, maybe they can't do it because by chance they rejected the null hypothesis incorrectly, or up to 1 out of 20 times. Okay, so now what else do I need to know here in order to calculate this? I need to calculate standard error, right? But in order to do that, I need a sigma, but I don't have it, so I got to use S, the standard deviation, and the only place I've got to get that from is the samples. So I get this, I'm going to calculate standard deviation for males. Okay, good. Okay, now I'm going to do it again for females. Good. That comes out to that. Okay, now I want to calculate my standard error. My standard error is equal to the sigma over the square root of the sample size. Okay, so that's a Q. Okay, square root of the sample size. Well, I got a problem. I don't know what sigma is, right? So instead, I'm going to use the standard error is equal to standard deviation of the sample over the square root of the sample size. I got another problem. I got 2 standard deviations. I got a standard deviation for one population and a standard deviation for the other population. How am I going to deal with that, right? Well, one of the things that we might say to ourselves is if the standard deviations are the same, if they're very close to one another, maybe I can help myself out a little bit by actually combining the 2 of them into a single standard deviation for a sample from a sample size 18, right? Kind of helps me out a little bit. In other words, I can pool them, put them together, right? The only problem is that they're never going to be exactly the same. So in this case, it's 2.7 and 1.94. Do you think, you guys, just off the top of your head, do you think that's close enough for me to say that they're the same? You would think not, right? But as a general rule, what we usually say is that if one is not double what the other one is, we're willing to roll the dice and say that we roll the dice a lot. That's our business here, right? Probability and statistics, we're rolling the dice all the time, right? We're willing to say that we'll assume equal variances. Okay, if they're more than double what the one is more than double what the other one is, we're a little bit more reluctant. We might be inclined to assume unequal variances. Well, how does it affect our calculations? On Blackboard again, there's another document. Okay, that document is called t-test variations, and you just saw this in the lecture. And in this, maybe I don't want to make that too much bigger. Okay, and in this one, we have formulas for situations where we want to calculate the z-score or the t-score. We don't know the population standard deviation, so we're usually looking at the t-score unless the sample sizes are very large, right? So we want to calculate a t-score, the number of the difference between the 2 means over the standard error. Now, the standard error is going to look like this, right? Standard error is going to be based on a pooled standard deviation and the 2 sample sizes, right? That's what we have over here. Now, that pooled standard deviation is basically a weighted average of the 2 standard deviations for each of the samples, right? And we calculate it from this formula, okay? Not that complicated, because let's take a look at it in our case. In our case, it's equal to, let's see, pooled standard deviation is equal to the sample size 9 minus 1. This is 8 times the standard deviation squared. What was the standard deviation? It was equal to 2.73 plus, do I have that right? Yeah, 2.73 plus the second sample, 9 minus 1 is 8, times the second standard deviation squared, 1.993 squared, over sample sizes added together, 9 plus 9 minus 2, 16. It's not that bad, right? It's just a little tedious. Let's do that. Let's give that a try. I'm going to do it right here. Equals, okay, I'm going to do the inside of this formula, then I'll find the square root. Okay, 8, right? 8 times, where is the first standard deviation? That times itself plus N2 again is 8 times, I got to put an asterisk in there. I think I'll get to that. 8 times this times itself. That's standard deviation times itself. I got to stick an asterisk in there. Okay, put an asterisk in there. Okay, and I'm going to divide this whole thing, which means I got to put the whole thing into parentheses. I'm going to divide this whole thing by the sum of these two sample sizes minus 2, which is 16. And it comes out to be 5.63. But now I got to take square root of that. Okay, it comes out to be 2.37. Well, let me see something here. Standard deviation of this group was 2.73. Of this group is 1.94. The sample sizes are the same, so it stands to, it seems reasonable. It's in between the two, right? Now, the sample size could have been different, so it would have affected where it came between the two. But now that is our standard, that's our pooled standard deviation, right? So now I'm going to go into our t calculation. So t, as always, t is equal to x bar 1 minus x bar 2 over the standard error, okay, which is the bottom of that quiz, is this number. Oh, I'm sorry, it's not that number, is it? It's equal, we'll calculate that in a second, right? That's actually equal to, that's actually equal to the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. Okay, so let's actually calculate this out. So the top part, the numerator, is equal to x bar 1 minus x bar 2. What's x bar 1? It's 10. Whoops. Equals 10 minus 7.55. And the bottom part is going to be equal to, well, it's going to be equal to the pooled standard deviation, which is this number. Whoops. Equal to pooled standard deviation times, let's see, now I have to find pooled standard deviation. I find the square root of the sum of those two. The square root, whoops, of 1 over, let's see, 1 over the sample size, which is 8. Was it sample size or sample size? Yeah, 1 over 9 plus 1 over 9. Close parentheses. I think that'll work. Oops, I got to put an equal sign in front of it, which is 0.477. So now the bottom of the denominator is going to be equal to the pooled standard deviation times the square root of the sum of the samples, 1 over the sum of the sample sizes, is equal to 1.99. So t is going to be equal to the difference in the two means, whoops, the difference in the two means divided by the standard error. And what does t come out to be? It comes out to be 2.18. Now, do I know if I can reject my null hypothesis yet? It's bigger than 1.96, right? Can I reject my null hypothesis? It's t. We have the same problem as always. Got to look up what the critical value of t is, right? So now what is the number of degrees of freedom here when we do this? The degrees of freedom is equal to n1 plus n2 over 2, which is 16, right? 9 and 9, 18, 16. Okay, so let's go to our t table. Oops, wrong one. Let's go to our t table and look up for 16 degrees of freedom. The critical value of t is 2.12. Right? Everybody agree with that? 2.12? Okay, so the critical value of t critical is 2.13. Can I reject my null hypothesis?
No.
Yes, because my critical, I've exceeded my critical value at t. I know there's less than 5% chance that I will be wrong if I reject the null hypothesis. So I reject the null hypothesis and accept the alternative hypothesis. Had this been 2.0, for instance, I would have failed to reject the null hypothesis. End of story. We don't make any conclusions about whether or not the null hypothesis is true. We just say we failed. But in this case, we reject the null hypothesis. Now, if I asked you, what would I expect the p-value to be here? Would it be greater than 0.05 or less than 0.05? Would be less than 0.05, right? Because there's less than the 5% chance. That p-value being bigger than the critical means that we have less than 5% chance of being wrong if we reject the null hypothesis, which means our p-value is smaller than alpha, our acceptable level of error, so less than 5%. Is it going to be a lot less than 5%? No, because look how close the t-value we got is to critical value. If we get a t-value that's exactly the same as the critical value, our p-value is equal to 0.05. The same thing as alpha. Now, every semester, some student asks me, well, what if the p-value is exactly 0.05? Can you reject the null hypothesis? Right? That's every time that comes up, I bring up, anybody here read Catch-22? No, nobody reads Catch-22 anymore. It used to be like a standard in college, you know? But Catch-22 is a story about World War II and these Air Force, these Army Air Force bombers. They used to at a base based in Italy during World War II, and they would have to go out on missions. And half the planes wouldn't come back from these missions. So they didn't want to go on them, so they would want to be on sick call if they could, right? So the deal in sick call was they had a rule that if you had a temperature over 102, you could go back to your bunker and sick call. If you had a temperature under 102, you had to fly to mission. Right? So if you showed up there with a temperature of 102, nobody knew what to do. So they would send you away for an hour and tell you come back, take your temperature again. Right? So it's kind of the same situation. It really doesn't make any difference, right? You basically would reject the null hypothesis, I would think. Okay, so at any rate, let's do the same thing now in SPSS. There's a file in here on Blackboard, which if you right click on it and download it, can drop it on your desktop, which is tosampletest.sav. Let me do it on time here, okay? Okay, let's open up SPSS. Okay, I'm going to open that file. Open, data, navigate to that file. On my desktop, it's in that folder, data sets, sample t-test. This is the same data that we just worked with. Okay, there it is imported. You may notice that on some of you that open it, might, instead of seeing the gender, under the gender variable, instead of seeing male and female, you may see numbers there. That's because if you go up to view, there's something called value labels, a toggle. You can toggle that on and off if you want to see what's actually input there and what it represents. If I go to the variable view, you can see for gender that under values, we've identified 1 represents female, 2 represents male. Okay, so I'm going to go back to the data view just for the hell of it. And it's the same numbers as we were working with before. So now I'm going to go into Analyze, Descriptive Statistics. And you know what I'm going to do before we actually do the analysis? I just want to see what the means of these two, see if I was right when I calculated the means and standard deviations before. So I'm going to go into Descriptive Statistics. If I go into frequencies, that's really only good for categorical variables. How many males, how many females there are. Descriptive statistics, that really just gives me the averages, standard deviation for everybody, doesn't split it up into male and female. If I go into Explore, that'll allow me to divide the data up between the two genders. So in the dependence list, I put my numerical variable. And in the factor list, the way I want to break it up or factor it, I put gender for male and female in this case. Okay, and I say to myself, okay, let's go ahead. It's going to do statistics, calculate 95% confidence interval, do all the statistics and so on, descriptive statistics. I'm going to click OK. My output window opens up. And here in my output window, I can see that the mean for females was 10. The mean for males is 7.56. These numbers should look familiar, right? The standard deviation for males was for females 2.739, same as we got. Standard deviation for males was 1.94. So we can see that our calculations were accurate. Of course, we did it in like 1/100th of the time it took to do it in Excel, right? So this is why we like programs like SPSS. What's that? I don't think so. Did I mess them up? I don't know. You tell me. Did I cross it up? You want to know something? For our purposes, it really doesn't make a difference, right? Because we're just looking for a difference. So you could be right. They might be the opposite. But for our purposes, I'm not going to be concerned about it for right now. So okay. So now I'm going to do my analysis. I'm going to compare the means of these two samples. Analyze, compare means. Okay. Now, one sample t-test. That's what we did before. Just take a look at it. Okay, in that case, I would put my variable in here, and then I would tell it what value to compare to. So for instance, when we did it before, the value that we compared it to was, I think, 7.4 or something like that, or 9, 8, or whatever, right? So that's for a single sample t-test. In other words, you'd be comparing the X bar from that sample to a set value, a known value for another population, single sample t-test. We're not doing that. This time we're doing a two sample t-test. That's going to be under here, analyze, compare means, independent samples t-test. So I'm going to click that, and it's going to give me an opportunity to put in my numerical variable, and then to put in the variable that I'm going to group them by. In this case, it's the categorical variable gender. Now, unfortunately, I do have to tell it what the numbers are, not just male and female. So I got to tell it 1 represents one gender, 2 represents the other gender. Okay, and I'm going to say, okay, I'm going to look at the options. 95%, good. Okay, that's for a 5% alpha. Okay, I'm going to click OK. It does a calculation for us, and I'm going to pull this up a little higher. Oops. Where'd it go? Okay, I'm going to pull this up a little higher. Let's take a look at this. First of all, did I assume equal variances or unequal variances before? I assumed equal variances, right? We used that first page, which was assuming equal variance. That page, that pooled standard deviation, that was for assuming equal variances. Okay, so if you look here, that's the top line here. It actually calculates the t-score. Here's the t-scores. It actually calculates them twice. So the first time it calculated equal variance. So I'm going to stick with that top line for now. So the t-value is 2.184, which is what we calculated when we did it as well, right? When we did it by hand. Okay, now the degrees of freedom is 16. It used the same calculation that we did to determine what the degrees of freedom would be if we assume equal variances. Use the rules on that page. Okay, so now what did it do next? Well, in this case, we were only able to say, because we used the table with just the critical value, not the whole distribution for that sample size for t, but just the critical value, we were only able to say that the probability of being wrong if we reject the null hypothesis, in other words, our p-value, is less than 5%. In this case, SPSS can actually tell you what that probability is. The p-value, or the probability of being wrong, is 4.4%, 0.044. Okay? So we get a little bit more information from this. And as we suspected, it's not a whole lot smaller than 5%, right? We just barely got below that threshold. Although we might have, if we're 5% or a little bit more, we might have rejected anyway. Okay, so now what if these were unequal variances? What if the variance of one group was more than double the other one, the standard deviation, more than double the other group? Well, in that case, we would have used the line below. Okay, now that's kind of a rough rule, that double or not double. It's kind of a rough rule, right? In actuality, SPSS has a test that you can use. If you look at this part over here, okay, where it says Levine's test, I'll read it for you if you can't see it too well. Levine's test for equality of variances. And it has two boxes here, F and significance, another p-value, another probability, right? Well, the way that this test for the equality of variances works is the top line assumes equal variances. The bottom line assumes unequal variances. Normally, when we do a statistical test and we set up a hypothesis, what's our starting hypothesis? Our null, that they're equal, right? So the top line, that they're equal, is what we're going to use unless this Levine's test gives us enough ammunition to reject that null that they're equal and use the alternative that they're unequal. In other words, the bottom line. So what is our p-value? Anybody? Can you guys read it? I'm sorry. Our p-value. No. P-value for Levine's test is the box is here to the left. The p-value, the F statistic is 1.5456. The p-value is 0.245. Can I reject the hypothesis that the two variances are equal? No. So I'm going to stick just like I did with my rough estimate that they're not double. I'm going to stick with the top line and use that t-score and that significance for to calculate my p-value and my t-score and decide whether to reject the null hypothesis. Had this significance here been less than 0.05, I then would have rejected the notion that they're equal variances and said they're unequal variances and used the bottom line. I'm going to show you a quick look at that document that has all of those formulas for these different situations you might be in. So this first page is for samples with two samples, standard deviations assumed to be equal. The second page is for samples with standard deviations not assumed to be equal. Our rough estimate of that is if one is at least double the other. In that case, we calculate the t-score. We don't calculate a pooled standard deviation. We calculate the t-score as x1 minus x bar 1 minus x bar 2 over the standard error. In that case, the standard error is the square root of the standard deviation of sample 1 over n1 plus the standard deviation over squared of 2 over n2, and take the square root of the sum of those two things. A little bit simpler of a calculation. However, the calculation for the degrees of freedom is nuts, right? You can see it there. It's a ridiculous formula. That's why we were saying that we would just say the smaller sample minus 1. In other words, if we have 9 and 9, we would just use 8 as the degrees of freedom. That's a conservative estimate. Okay, so now I'm going to show you something here. If we had rejected, and go back to SPSS, if we had gotten a significance small enough to reject the idea that the variances are equal, and we used the bottom, well, the t-score would have been roughly the same. Our significance would have been pretty close, roughly the same. What about our degrees of freedom? Look at the degree. SPSS actually calculates that ridiculous formula, and that's why whenever you look at unequal variances on a t-test, the degrees of freedom is going to come out to a very odd number, non-integer, where when you use equal variance, it's always going to be an integer. Okay? Makes sense? We can try one now. There's another, I'm going to go to SPSS. There's another data set there that's similar to the one that we're working with, except that it has unequal variances. Data, and it is data set, open, data. It is 2 sample t-test unequal variances. We'll click open. Okay, looks similar, right? But it's 9 females, 9 males, except that the numbers are a little bit different. I'm going to do descriptive statistics explore. Okay, just so we can see what they look like, those numbers. Gender winds up in the factor list. I'm going to say okay. Okay, let's see. For females, the mean is 10. For males, the mean is 7.6, pretty much like we saw before, pretty close to what we saw before. Except this time, The standard deviation for the sample of females is 2.73, and the standard deviation for males is about 1. 1 versus 2.7. 1 is more than double what the other is, right? So I would use that second page for the formulas that I would use to calculate the t-score. Okay, well, we're not going to have time to do that, but that's how I would handle that. If I did it in SPSS, let's see what the result. I'm going to go down to Analyze, Compare Means, Independent Samples t-test, and I'm going to move the values into the test variable, gender into the grouping variable. Now, unfortunately, you got to tell it that 1 represents one of the variables, 2 represents the other. It's a little bit extra work. Click OK. Okay, and this time, if you look here, let's take a look at this Levine's test for quality of variance. I'm going to start with equal variances assumed. F is 7.896, right? A bigger number than before. And the significance, the probability of being wrong if I reject that, is only 1.3%. It's only 0.013. So I reject that hypothesis that they're equal variances, just as I would have if I calculated it by hand, and go down to the bottom and use the bottom formula for our calculation of our t-score and our significance. This significance is for this to decide whether or not you use the top line or the bottom line. If it's less than 0.05, use the bottom line. Okay, this t-score, these t-scores and significance are the ones that you're using for your actual t-test. So try not to get them mixed up. Okay, you guys okay with this so far? Okay, I'll do one more thing. Right? And that one more thing is I'm going to take a look at the idea of, well, what about when you have paired samples? When you get a situation like, let me open one up. Open. Data. Okay, paired samples. How about this situation? This is every person in this, there's 9 people in this study, not 18, there's 18 numbers, only 9 people. They gave each person, maybe it's a weight loss drug. And this is, well, you're not going to see 6s, I guess. Whatever these numbers represent. For maybe a month, person took a placebo. For another month, person took the drug. Now, it was a blind study, so they didn't know which one they were taking. But the value of this is that you actually see the performance of the placebo and the drug in each individual, right? So it's a little bit stronger of a study than having 2 random sets of people where, one person could react to a drug one way, another way. This is actually looking at how a person responded when they took the placebo for a month versus a person when they took the drug for a month without knowing which one they were taking. Okay, so now in this case, we're not really interested in the fact that patient number 3 had a blood level of 8 when they took the placebo and 4 when they took the drug. We're not interested in those actual numbers. We're interested in what the improvement was. What's the difference, right? So for each one of these, we will subtract one from the other to find only the differences. And what we're interested in, if there's no difference between the performance of the placebo and the drug, the average difference in each person, the average difference that we would get for all these 9 people, right, that third column, would be 0. So the test we're going to do is a single sample t-test, except we're going to test whether or not it's different from the value 0 instead of different from the value of some other known mean. So I would go in here, Analyze, Compare Means, Paired Sample t-test, and I'm going to move both. Notice it wants 2 variables, placebo and drug. Both have to go in there, right? And then I'm going to say, okay, it does a calculation. And here's our paired sample t-test. And the mean difference between these two is 1 point. In other words, those 9 numbers, the differences, is 1.56. But is that really different from 0? No change. Standard deviation is this. The standard error is 0.89. What's my t-score? My t-score is 1.730. My degrees of freedom are 8, and my significance is 0.122. Can I reject my null hypothesis? No, I can't. And since this is a single sample t-test, if I wanted to know if my t-score was big enough to reject my null hypothesis, I would go to the t-table, look up what the t-critical is for a sample size of 8. I happen to remember it's 2.306. And I noticed that my t-score for this test does not exceed the critical value. So both the small t number and the big significance p-value tell me I can't reject the null hypothesis. Okay? So hopefully this is all recorded. So if you want, you'll be able to play it back at a lower speed. You know, they have like some of these movie players. I think you can even on YouTube. I think you can hit like minus 0.5 or something like, and you can listen to it slowly. I think I'm not sure if you can do that, but with these YouTube videos. Okay, and that's 7:50. So I think we need to quit. Oh, you guys are in shock, right? Is that it? Or I think it's the change in the time. That's got to be it, right? It's definitely like a little seasonal affective disorder. A little, you need to go home and sit under a sunlight, one of those sun lamps for a little while or something. Good night, guys.